Okay. All right, so for your programming test 1, as I said, I'll try to get back to you by the end of Friday. I'll check with the TA, also finalizing the result. For your written test number 1 tomorrow, the guide, the example question, you can find it on the e-class. And there was some review session on Monday, a little bit brief, but I think you could still find some useful information there. But check it out if you might find it useful. Your lab number 3, I will release it tomorrow after your written test number 1. So you can take a look. Also get started. So lab number 3 will be somehow covered in the subsequent test, so you definitely want to get started as soon as possible. Office hour, I still got today, 3 p.m. if you want to speak to me. Otherwise, I'll see you guys tomorrow morning, right? Don't be late, 9 a.m. sharp. And don't forget, for your written test, you're going to need a dual mobile verification. So make sure you bring your mobile phone. Of course you will, but make sure that one works. You may just want to find some workstation in the prison lab and also try out your EECS logging and also the PPY logging, right? Both of them should work, right? You should be responsible for any time loss if your logging didn't work for tomorrow. Okay. Right, any question about the course? Very good. All right. Let's now do a quick recap and then we'll continue with the LTL. All right. So last time we actually spoke about if you're given some LTS, or like a visual LTS, some state diagram here, how can you really understand the pattern for the path, right? So we talk about some technique called unfolding and unwinding, basically just trying to see the patterns for the transitions, right? As soon as you can see some node that you have visited already, you know that the pattern is actually repeating. So we saw 2 instances of the repeating patterns. You can review that part of the lecture just to make sure you know how to do it. And we talk about satisfaction relations. There are 2 of them. I kind of mentioned to them at one go before I introduce them. But we've already done one of them. We're going to do the other one as well and compare to see how they're supposed to be evaluated. So for path satisfaction, you're basically given a particular path and trying to see if the path is going to satisfy some LTL formula. That's basically what we did last time. But we haven't really spoken about how you can check it against where you got temporal operators involved. That's something we'll do today. Today we'll do lots of examples to really make sure you kind of grasp the intuition about the 2 kind of satisfaction relation. The second kind, which I will introduce very soon today, is called model satisfaction. So rather than just one particular path, you're actually going to consider a particular state. You want to consider all the paths starting from that particular state. So since we say all the path, you can see there's a universal quantification hidden right here, right? That's something we'll see when we try to formulate this particular satisfaction relation. So as we'll do the example today, I will basically try for different temporal operators, you know, the X operator, the G operator, and the F operator. For each one of them, I'm going to start with the path satisfaction first and see how they work. That's a simple case, just a single path to consider. And then we'll move on to the model satisfaction, in which case you have to consider all the possible paths starting from a particular state. So that'll be the extra caution you have to make whenever you talk about model satisfaction. We'll get there, right? We'll do lots of examples. All right, so we talk about path satisfaction, and the only thing we did last time was about if you're going to evaluate some propositional logic, right? Propositional formula. You're using negation, conjunction, disjunction, and also implication. If the formula itself is actually complicated enough, for example, if you say phi 1 and phi 2, maybe each one of them is complicated enough, you can feel free to kind of break it down into 2 evaluations and put them into conjunction. Right? You can kind of decompose the formula into 2 parts and then combine their result together using the relevant operator. Can be conjunction, can be disjunction, and also can be implication. Right? So that'll be the easiest case for path satisfaction. And also, by definition, if you try to evaluate some propositional formula, by definition, it's just going to evaluate whether that formula, for example, this one here, whether or not it's true in the very initial states, which is S1. And by the way, the S1 here is not necessarily the name of the states. This one here simply means the very first states in the path, right? That's a formal way to refer to like indices. It's like a 1-based path sequence that's infinite. All right? And then we did the exercise about even number states, make sure they satisfy certain proposition. right? You can also review that exercise. Are you guys okay about this path satisfaction? All right, not too bad. In some way, path satisfaction for proposition is very straightforward. You only got to look at the first states only. But we're going to see that there are some other formulas where you have to look at the entire path somehow. And then we define the three temporal operators. We'll also review them because we're going to do examples about them today. We got the next operator, which is x. And also we got the global operator, which is also called henceforth. And also we got the future operator, which is also eventually, right? So these are the three operators we're going to start with. We still got until, release, and weak until. So these are the three operators we'll do hopefully next week once we finish the basic three. All right, let's now review them very quickly, one by one, okay? For the next operator, you basically are given a path. Let's say path satisfaction. Once you're given a path, you don't really look at the first states. Literally, next simply means next to the initial states. So you only look at the second states only. All right? By definition, you're just going to see if pi 2 actually will satisfy the phi. Right? That's why I asked you guys to really consider this orange formula here, which is what we are given. That formula there contains the next operator. We can interpret that by getting rid of the x operator. So we, rather than considering pi, we can now just consider pi to the power of 2. So we can just check to see whether this pi 2 satisfy the phi, which by definition, we can only look at the first state onwards. Right? That's one way to see it. And we also did some example about what if you try this particular evaluation, right? So here, it can be arbitrary path. So pi to the power of 3. Right? And then we said that it boils down into you just checking pi to the power of 4. All right. That also has to do with the little exercise we did earlier. Are you guys okay with the next operator? Okay. Yep. Of course, don't panic. It's not going to be covered tomorrow, but you got to worry about it a little bit later for the second written test. But take some time to digest, to learn. The second operator is the global operator. In some way, we're checking some invariant property for the system. We want to make sure all the states, or every state in the path, will satisfy this property. That's why it's globally true, or henceforth. So by definition, we can just use a universal quantification. So every index I, starting from 1. Because pi to the power 0 is not defined, as we said. So you got to start with 1. And then every state over here will satisfy phi. That's a global operator. That one is very straightforward, just one extreme. You want to make sure every state satisfies. As long as you can find one state that does not satisfy it, then you can disprove it. And by the way, for your math review lecture, right, which is going to be covered tomorrow, remember we spoke about the strategy for proving or disproving quantification, right? So this can be applicable over here, okay, which we'll see today. So in some way, there's a nice review about what you should know tomorrow. Okay, the third one is the future operator. That one there is more on the other extreme. So we don't really insist that every state in the past should really satisfy phi. At least one will be fine. At some time in the future. Can be very close future or can be very distant future. Since the path is infinite, as long as it's satisfied at one point, we'll be okay. Right? So that's why we got to exist quantification here. Okay. All right, and I think, yeah, that's the last exercise we did. That one there, we just took the path satisfaction relation, and then we just try to evaluate different propositional formula here, right? You can just try each one of them. Let's just take one, for example. When I was trying to evaluate this one here, so there are two possible approaches to go for this. If you find this one here, simple enough, you can just evaluate it right away. So since we got pi, which will be as if pi to the power of 1. That means we should really start with the first components of the states of the path, which will be starting from 0, S0. And then, since we are evaluating propositional formula, we only need to consider the initial state, S0. Does S0 satisfy P implies Q? It does, because we got the atoms over here, P and Q. Both of them are satisfied. The implicit missing R means not R is satisfied. It's not satisfied, basically. Right? So when you say P here, it is here, so that should be true. And the Q here, that's also listed here, so that should be true. True implies true will be true. Another way to see that would be, you can decompose it into two separate satisfaction relations. You can break this one here into here, evaluate it, break this one here into here, and evaluate it. And this one here, since P is here, true. This one here, since Q is here, that's also true. And then you try to combine them using the implication. So you will get the same result. Right? But in this case, P and Q themselves are individually pretty simple. You don't really need to decompose. You might want to decompose if the antecedents or the consequence is sophisticated enough. In that case, you may want to evaluate them separately to help you. Okay. That was the last example we did last time from Monday. Any questions? We're good. All right. So this page here, I said 1.1 because it's actually part 1 of exercise 1. Part 1 only talks about path satisfaction. And part 2, we're going to basically try also propositional formula, but we're going to try model satisfaction. But let's now define model satisfaction formally so we can go ahead and do the comparison and evaluation. Okay? And when you look at the iPad notes, you will see that I also put the slide number over here, so you can also go there. So the example we did covered the one that's on the slides, but also we did some additional example as well. So you can definitely look at both to get more exercises. All right, let's now start by defining the model satisfaction. Okay, let's look at the slides first of all. Okay, you should look at slide 35. So 34 here is just the definition for the 3 basic temporal operators. So 35 is the definition for model satisfaction. So what we're given is a model, label LTL, label transition system. Again, that's going to be covered tomorrow. You got set of states, you got transition relation, you got a labeling function, right? And also, let's say we're given a state, and the state is a valid one. A valid state would be some member of the S over here, right? You cannot just give arbitrary states. It may just be undefined. So it got to be a member, a valid state. And we got some valid formula, something that's syntactically correct, which you guys also know very well. All right, so the way to really write model satisfaction is you will write, well, to be very complete, you got to write the model itself, the LTL, and also the states. But when the model is very clear in the context, you don't have to keep mentioning about the M. It should be quite clear in the context usually. So you only have to mention just S, the states we're talking about, as opposed to a single path. So what do we really mean when we want to evaluate the satisfaction? And this symbol here is being overloaded. So we're using the same symbol for both path satisfaction and also model satisfaction. Just notice that, right? The same symbol. All right, it will be true if and only if every path in the model, in the label transition system, starting at the S, which is input, will actually satisfy the phi. So the way to define model satisfaction is to quantify over all the possible paths starting at a particular state, and then we use the path satisfaction afterwards. Okay, let's now take a look. All right, let's now just review that quickly, and then we'll do examples. So what we're given is we got a label transition system, we got a valid states, right? Again, you want to be very clear. The S here is just the S here, right? So we talk about relevant states. And we got something that's syntactically correct. So we say every path. Whenever you see every or all, that's really universal quantification implicitly, right? Every path. Okay, basically for all. All right, starting at S. So you can see that this S over here is corresponding to the input right here. Okay, especially here. All right. We'll talk about proving or disproving once we see the formulation using quantification. But let's now formulate it. Since we say every path, right? The way to write down the notation, let's do from scratch. You have a single state, right? And then you say that that one satisfies. So here we talk about model satisfaction. Model satisfaction. And here we don't really need to mention M again if M is quite clear in the context. Where M, the model, is clear in the context. All right. So after the satisfaction relation, we're going to say some LTL formula. So I'll just say phi right here. So what we have is S satisfies phi. That's the formula. It's going to be either true or false. Okay? So if and only if. If and only if, all right, for every path, pi, all right? And then let's put it a little more informally. So pi should be a valid path in M that starts with S. So here, let's write down informally. You can say pi starts with S over here. And if you want, you can also say S is a member of capital S. You can also say that. It's a valid state. You can include that too. But that one, it should be quite clear. And then we say if that's the case, then we will care whether or not pi will satisfy the phi. And notice here, this particular relation here is about path satisfaction. So this is what I really meant earlier to say. In order to define model satisfaction, we have to use path satisfaction by quantifying over all the possible paths. Right? That's really what I meant. And this part here, we can make it a little bit more formal, okay, just for this part. When you say pi starts with S, basically we just specify the pattern for the path, right? We're just saying pi equals some sequence which can be infinite, but it has to start with S. Right? Just that. As simple as that. Right? All right, that's a formulation you guys have to remember. The most important for you to remember is as follows. Whenever you're doing model satisfaction, you already got some universal quantification at the first level. If the temporal formula itself got also universal quantification or existential quantification, you got nested already. Even worse, if you try to nest temporal operators together, you might get even more, right? Not too sure about today, but definitely Monday the latest, we're going to see one example where we got triple level of quantification. And once we get to that formulation, I'm going to walk with you about how you can prove or disprove that particular pattern. Right? We'll get there, right? But everything is going to be put together. That's really the important thing. Alrighty, so now given this given this model satisfaction, how do we prove or disapprove about this one here? Right? In order to really see how to prove or disprove, you have to just make sure you understand that we got some universal quantification. Okay? For tomorrow's test, you guys should know how to prove or disprove, right? I hope, okay? Maybe you haven't got there yet to study. Hopefully you'll catch up today, right? Okay, let's just get to the point. All right, how to prove it? Basically, to prove universal quantification, you got to do most of the work. You got to make sure you show that every path or every path pattern will satisfy phi, okay? To prove S satisfy phi, we need to show that every path, and I'm going to put in parentheses or pattern, because strictly speaking, you cannot really show for every path, because path might contain cycle, in which case you can only observe the pattern for the cycle, right? So that's why I put pattern here, which you will see example. Every path pattern pi satisfies phi. All right, basically the formula, right? You just gotta consider for every pattern. That's how you prove it. All right, guys, help me out. How do we disprove it?
Witness.
Okay, go ahead.
You give a witness.
Witness, which will show.
It disproves it.
Okay, let's be a little bit more precise. When you say witness, what kind of witness?
Counterexample.
Do you find a witness states or do you find a witness path? Witness path, because we are now quantifying over a path, right? Exactly. Okay, very good. I'm pretty sure that's Adrian was want to point out, right? Okay, to disprove. Okay, to disprove the model satisfaction, you have to provide a witness path pi such that it is not the case that pi satisfies phi. And by the way, this expression here, if you prefer, you can also write it as this. Pi not satisfying phi. They mean the same thing. Okay? I just put negation, either rapid or not rapid. It's completely up to you. Right, very simple, right? Just a very simple application about universal quantification. But once we get to the nested formula, that will just get a little bit more complicated, which we can still deal with. You just got to be more cautious. All right, so from now on, we will be able to do lots of examples, hopefully at least until the end of today, right? We'll just do as many as we can, okay? But let's be careful. So we're going to do basically path versus model satisfaction. So we have already done the path satisfaction last time, right? So that's the one we did from last time, right? I just just recap it in the beginning. Let's now do the very similar example, but we do model satisfaction. Okay. Right here. All right, so that's why I say it's 1.2. You can also look at slide 36 for some explanation there, but I'm going to just say that anyway here. If we look at this one here, number one, why are we talking about model satisfaction? So you got to look at the left-hand side of the satisfaction relation. The left-hand side are all the states rather than path. That means we're talking about model satisfaction. That's number one. So for all the left-hand side over here, you can see they're simply just states. S0, which is valid states. So here, capital S should be a set containing S0, S1, and S2, right? That's the LTS. And since we are now putting the states to the left-hand side of the satisfaction relation, is a model satisfaction. So here, if you look at the symbol right here, so we know that it is model satisfaction. More specifically, we have to consider all the paths starting from S0, right? All the paths starting S0. But we are lucky for this page over here. When you talk about all the paths starting from 0, and by the very definition for checking propositional formula, which state do you look at? Just the first states. In which case, it doesn't matter which path you're talking about. You will be S0 anyway. Right? I'm going to write it down for you. When you talk about all the paths starting from 0, all such paths, pi has S1, oh, you know what? Has pi to the power of 1 being S0. That means we only need to consider this. Only need to consider S0 to evaluate propositional formula. It's only the special case for propositional formula because we only need to worry about the very first states, even though we have to consider all the paths starting from S0. But since we are only considering the first states, they're all S0, right? So it boils down back to the same problem as before. Right? But you got to understand why we can reduce the problem back to 1.1. All right, so it's going to be very straightforward because now we got S0 over here. So that's the only states that we're going to consider. And the answer will just be the same as before. Okay. So let's now do very quickly. So every state, S0, of course, is going to satisfy true. Not a problem. S0 doesn't satisfy false. That's also true. S0 satisfy P and Q. Yeah, I agree. Satisfy either P or Q, of course. Satisfy P implies Q because true implies true, right? Satisfy R? No, because R is the only one that's missing. So we got implicitly not R. So that one should be false. Okay, finally, what about here? Because R here is known to be false. False implies anything. That will still be true. All right. So we know that this one here is actually false. So that means the whole thing over here will just be true. Of course, you can also feel free to decompose the formula into two and then apply the implication. It's up to you, okay, if you want to. Not a problem. Are we good about this? I think that the main thing to grasp from this page over here is, yes, to start with, you have to consider all the paths starting from S0. But since we're evaluating propositional formula, we only have to consider the first states for every path, which is going to be S0 anyway. Okay. And why don't we sketch exercise? Well, it's assigned to you, but let me help you a little bit. What if we change the left-hand side here from S0 all to S1? All right. Think about it for one moment, and then I'll give you some hints. So I'm going to write it down here. So for example, you got S1 satisfies true, S1 satisfies false, and also S1 satisfies P and Q, S1 satisfies P or Q, etc. Okay, that's what I want to do. Okay? The only thing I changed was S1, right? But it's still model satisfaction. Okay. Yeah, go ahead. P and Q will change to false. I agree. Why?
Because S1 doesn't have P.
Yeah, exactly. That's basically right. Okay. I think your fellow student was exactly right. I just want to say one thing here very quickly. So here we're talking about model satisfaction, meaning that we got to need to consider all the paths starting S1. And since we are in the special case where we're evaluating propositional formula, we only need to consider the first states of all such paths, which will be S1 anyway. So we end up considering only S1. All right? So for this little exercise here, it's going to be S1 that we're going to consider just for the very first one. All right? Just this one here. So as your fellow student said, let's say P and Q not going to be satisfied because Q, R are listed. That means implicitly we got not P, right? So P and Q is going to be false. P or Q will be true because Q is listed right here, right? So that'll be true, right? Yeah, think about this exercise here, and I'm sure you can do it. Okay. If you have any doubts about this one here, you can feel free to reach out to me. And of course, it will be also very conceivable if you try to do another exercise yourself by changing from S1 again to, how about S2? Very similar. You can also give it a try. Okay. So now we are done with basically path versus model satisfaction for propositional formula, in which case we only need to look at the first states only. Okay. Alrighty. Let's now move on. So now we got 2.1 and 2.2. Oh, sorry, go ahead. Yeah. Yeah. Okay, sure. Why don't we do that? Okay. So for that one there, so let's say, let's do that one. Let's say we got S1. And we got P implies Q. Okay, let's say for this one here. So P apparently is not satisfied. In that case, we got false antecedent. False implies anything, so it would be true, trivially. Okay. So this one here is going to be false, so it will be true. Why don't I do from completeness for you? So here, let's say S1, the last one. So R implies P and Q and R. Guys, what should this be? False, okay? Because R here is actually true, right, in S1. But you got P being false, which is going to make the conjunction false. So you got P implies false, right? Very good. So what I would do for you is you can see the R here is actually false because it's not there. And P also is false. Since you got here is going to be false for the conjunction, you got false. Oh, R is true. I beg your pardon. Okay, my bad. Okay, let me do it again. Yeah, of course. Sorry about it. Because you got R here, so R is going to be true. Absolutely. And then you got the P here is actually false. All right. So you got this conjunction here being false. So true implies false is going to be false overall. Okay, I think this is nice to actually do. Okay. All right. If no further question, why don't we do another pair? Good.
If we replace S1 with Pi1, would it be the same?
If you replace, in this case, it would be, no, it's not the same. Okay, good question here. So in this particular scenario, we're checking propositional formula, right? When evaluating propositions, okay, you were asking if I check to see S, you said S0 and Pi1 or S1 and Pi1?
Like to replace S1 with Pi1.
Okay. For example, P. Okay, you're asking this, right? Okay. Any answer? It's a good question. I like it. Go ahead.
It wouldn't be the same.
How come?
Because S1 here is a state, but when it comes to Pi1, it could be any of the path, but the first state of that path.
What's the first state of that path?
That would be according to that path.
According to a
Let's say if
path,
we-
right? Mm-hmm.
Yeah, let's say if we start with S0 and we go to S2, it would be S2. And
Okay, very good. Okay, that's exactly right. Okay. So here, in this case, you're being very explicit about which state it is, right? It's S1 right here. But here, when you say Pi1, I don't even know what pi is, as your fellow students said, right? For example, if the pi looks like, let's say here, if the pi looks like S0, S1, for example, right? In that way, if you say Pi1, you're basically having just the same path. In that case, the first state would be S0. So you're not checking S1, so they are not the same. Right? In fact, for this particular diagram, the first state should always be S0. There's no path that will start with something that's not S0. Right? So they are not the same in this particular example. Okay? So what I would do is you can think about that's the example here, and then I would say this will be as if we check to see S0 satisfy P. Right? S0 is the first component in the path. Okay? All right, very nice. Guys, any more follow-up? It's important you understand. All right? Alrighty, let's now move on. The next pair will be about the next operator. And we're going to do as in the following sequence. So you see 2.1 and also 2.2, right? These two, 2.1, 2.2. 2.1 is about the path satisfaction. You will see some pi there. And also 2.2 is about model satisfaction. You will see some state over there, right? They're very clear distinction. But let's just make some very quick annotation. So for this satisfaction here, it's really about path satisfaction. And for this one here, it's more about model satisfaction. And for this one, I can tell you it's not going to be trivial anymore for us, right? I'll just give you a little bit preview, right? For model satisfaction, we have to consider all the paths starting with S0. But we don't consider initial state anymore because it's the next operator. We should consider the next states, like a second states. Is there only a single second state in this case, starting from S0? Not really, right? Because the second state could be, for example, if I start with S0 right here, second state could be either S1 or the second state could be maybe S2. So these are the two possibilities. All right, so it's no longer trivial, but we'll get there. All right. Let's now try to look at this one here, and then we'll evaluate. Okay. And we're talking about this pi here, right? This particular one, right? You're given. And by definition, you're just going to look at if pi to the power of 2 satisfies the phi. So we can disregard the next operator, right? First of all, let's annotate what's pi 2. Pi to the power of 2 is basically this path over here, starting from the second components, right? Right there. So this one here is pi 2. And once we get to that pi 2, we can worry about true, false, Q and R, Q and R, Q implies R, Q implies R. You're going back to where you feel comfortable, right? And let me just say the first one. The first one there, pi, this will be if and only if pi 2 satisfies satisfies true. And if you want to evaluate the proposition over here, basically you will just have to look at the second states, which will be here. Oh, sorry, just over here, S1, right? The first states for that particular true. Every state satisfies true. So all you got to look at will be just S1. So S1, I'm just going to highlight it. And why are we not considering S2? Because it's not part of the path, right? We're not considering it, just in case you're wondering. Okay, so all we got to consider will be S1, which is the next states for this particular path, right? And false is always not satisfied, so we are fine with it. Right? What about Q and R? That's right? Because S1, both Q and R are there. All right, very good. Aha. Guys, how about this one here? This one is interesting, huh? This one has to do with your syntax study, right? We talk about precedence over here, all right? So this one here, we are saying we get to the next states, which is S1, and try to evaluate in S1 whether it satisfies both Q and R. That's what we're doing. And this one here is a little bit different. What we're doing is we say, with respect to pi, which is over here, we want to evaluate two things. Number one, we want to evaluate to see whether the next states, which is S1 here, does it satisfy Q? It does. And the R here is not going to be evaluated in the next state, not really, because it's now wrapped within the next. Well, we're going to evaluate which is R itself, in which case we're asking whether S0 will satisfy R. All right, that's what it is doing. So what I would do is I'm just going to break it down into this. So think about this is one and this is another one. So what we're saying is pi satisfies next Q, and also pi satisfies R. So this is one scenario where it's actually nice to decompose it so you don't really get confused. Okay? And then we know that for this one here is basically pi 2 satisfies Q, in which case we are looking at S1. And this one pi R, just pi, in that case we're looking at S0. Okay, just don't get confused. All right, we said this one is true, and this one here is false, agree? Because R is not satisfied there. So this part here is actually true, and this one here is actually false. So overall, you get false. This one is actually nice. A little bit trickier, but it's doable. You just got to watch out. You want to apply what you learned earlier about syntactical analysis and see which order should really go for evaluation, right? All right, the next two pairs, the next two is pretty similar, but let's still do it, okay? This one here, we're going to apply the X to Q implies R. So that means we should go to S1, evaluate to see whether Q implies R is true. Is it? Yeah, indeed, because both Q and R is true, right? So this one here will just be true, right? Because both Q is true and R is true. True implies true. How about this one here?
False.
False? How come?
Because you're looking at by two satisfies Q,
Uh-huh.
implies by satisfies R.
Mhm.
So it's true.
Yeah, you got to decompose. Sure, no problem. So let's see here. If and only if, we can say pi satisfies xq implies pi satisfies R. All right? So pi satisfies R. We're asking whether or not it's satisfied in this state. No, it's not there, right? So that one should be false. On the other hand, if you look at pi satisfy next q, that one there would be as if we say pi 2 satisfies q. Does this one satisfy q? Yes, right? That would be true. So we basically got true implies false, which is the only way to make implication false, right? So overall, it's going to be false. All right, good. Yeah, so you guys can pay more attention to these two. This one here, and also this one here, right? They're more interesting. You just got to watch out the precedents. Right, the exercise for you to try will be here. What if you change the pi over here to be 2? In which case, of course, relative to pi to the power of 2, if you look at x, it's going to be the next stage from there, right? So that's something you're going to try it out. Okay? Exercise. And I'll try to post the solution a little bit later, but you guys can try it out. I'll put exercise here so I remember which part to update. Okay, exercise. Give it a try. Okay. Basically, copy all the formula here. You just put the left-hand side over here to be pi 2. That's all you got to do. Okay. Let's do one more, and then we'll take a very short break, right? And then we'll continue. Okay. So this one here, we're actually going to do the model satisfaction. So we're going to consider all the paths starting from S0. So we're going to consider all the paths starting from S0. And let's now do a little bit exercise of enumerating them. You don't really have to unwind. You don't need to. It's not necessary. Let's try to figure out the different patterns over here. All right, so number one, let's try different ones. For example, let's say if you simply got S0, S1, S1 back to S0, you're not just infinite, right? So one will be if you got S0 and then S1 and then S0 and then S1. Just repeating. And then you can say, for example, let's say you go from S0 and then you just go to S2. Once you get there, you just get stuck. Okay? And then somehow you have a way to really go from S0, S1, and S1 to S2. But we can make it a little bit more general. It could be that you want to go for as many circles as you like, and then you decide to go to S2. Once you go there, you get stuck, right? So that's another way. So you can say you basically want to go for as many cycles as you like, and then once you go there, you're going to go here. Okay, so I'll put it here. So you can go for S0, S1, S0, S1. Okay, I'll just say dot, dot, dot. As many cycles as you like, and then you come back to S1, and then you decide to go to S2. After that, you just get stuck. Exactly, like that, right? Alrighty. Of course, you can also expand this one a little bit. You can say after S0, S1, S0, S1, and you decide to go to S2. You can also change that a little bit. You can do that too. All right. All good. So now relative to S0, so now we know about the path pattern, roughly. And then since we are considering the X operator, so that means we only have to worry about the second states, which will be either S1 or S2. Agree? Okay. So these are the next states of the path starting from S0. So when you evaluate the path, when you evaluate the model satisfaction, conceptually you have to make sure every path is going to satisfy the formula. But essentially we are checking to see every second state here, which can be either S1 or S2. Each one of them should really satisfy the formula. That's what we're checking. All right? So basically we are checking to see these propositional atom, okay, are they satisfied by S1 and S2? Because, let me remind you very quickly, when we talk about model satisfaction, it must be a universal quantification. So that means both of them should be satisfied. If one is not satisfied, then the whole model satisfaction is false. Okay. Let me just make one more annotation for you. So the next over here tells us only need to consider S1 and S2, because S1 and S2 are the next state, right? So we're just trying to break it down, to different pieces. So now all we got to do is we're going to look at these propositions against S1 and S2, and both of them must be satisfied. And for true and false, doesn't matter what state you're talking about, right? So this one will just be true, and this one will be true as well. All right. And since we talk about S1, S2, let me just highlight them. We got S1, and also we got S2. Okay, these are the only two states we got to worry about. Okay. What about Q and R? True or false? Well, if you evaluate Q and R in here, it is true. However, if you evaluate Q and R here, it's false. There's no Q, right? So there's at least one path that does not satisfy it, right? So the model satisfaction overall should be false. Are we following? Okay. If you believe that the model satisfaction should be false, what should we provide? A witness. All right? Exactly. Okay. And when you say the witness, you don't just say S2. S2 is not a witness. A witness should be a path. All right? So here it's going to be false. So you're just going to supply a witness. And we know that S2 is going to violate it. So you can say the path will be, for example, S0 and then S2. S2. And then you can just say for S2 over here, it only satisfies R. Okay, that's one witness path. Are we okay with this? Okay, very good. Okay. And what about here? Oh, this one here is a bit, okay. I just noticed what I did. Okay, I want to be more careful here because the X operator only applies to here. Okay, let me circle it again. Of course, this will apply to here. And, okay, let me just use highlighter. Apply to here, apply to here, apply to here, and now only apply to Q. And then apply to here, and then only apply to Q. Okay, gotta watch out for the evaluation. I didn't pay enough attention. All right. All right, let's now look at the next one. Okay, 3 more, and then we'll take a short break. What about this one here? False? Okay, sure. So for this one here, we got to look at basically for Q, we are going to look at for S1 and S2. Apparently, it's not satisfied by S2, right? Yeah, and this one here is already false. Or another way for you to argue is to say, since the very first state will be S0, that one does not satisfy R. You can also argue that way. Okay? You can argue either way. I'm going to give you both. Bottom line is false. So there are 2 possible witnesses you can give. Witness number 1. You're going to show that this formula here is actually false. In which case, you can just go for S0 and then S2. Right? So for S2 over here, apparently it does not satisfy Q. Right? That's one possible witness because of conjunction. Right? And then the second possible witness you can give will be you want to show that this evaluation is actually false. But that one has no next states. So that means we have to go for S0. But S0 does not contain R, so that's also false. All right. Number 2 will be the S0, for example, S0, you can give the same. In which case, you can say that S0, the initial state, does not satisfy R. Okay. Not satisfy Q. And this one here, not satisfy R. Right? Either way is fine. All right, for completeness, let's do 2 more. All right, for this one here, we're going to evaluate S1 and S2. Q implies R. For this one here, Q implies R, fine. For this one here, Q implies R, also fine, right? Because Q is implicitly false. All right, this one's good. All right, so you guys got to know the reason, right? I kind of sketched that already, but in the, maybe not in the written test, for sure. Not the coming one. But for the exam, if I ask you this, so to really argue about this, you should really show every possible path, right? Pattern. And show that why this implication will evaluate if true. Final one. And this one here, as you can see, we got 2 parts over here. So if I say S0 and then I want to evaluate R. R is simply just false, right? That one we know from before. Okay, what about next Q? True, right? Because, oh, are you sure? Next state will be actually S1 or S2, right? So S1 I agree, but this one no, because this one here is not satisfying Q. So we got some witness to show that it's false. John, you okay? Okay, I just want to make sure, yeah. You seem to be suspicious about it. All right, so let me put it down. So for this one here, all right, for this one here, okay, I'll put it here. This one here is actually false, in which case I'm going to give you a witness. A witness will be S0, S2, S2, etc. And we know that S2 here does not satisfy Q. So what we get is we got false implies anything. That would be true overall, right? So the whole thing over here is just going to be true. All right. And similar exercise you guys can try by replacing the S0 right here by S1. All right, and then of course you got to consider all the possible paths starting from S1. Okay. I can tell you that next operator is actually in some way trickier than the future and global operator that we're going to do after the break. So if you don't find this to be too challenging, that's a good sign. Right? It's not too bad. Yeah. All right, if no follow-up, why don't we do a very short break and by taking attendance. All right, just get your iClicker ready. All right, so in case you're looking at the slides, I think before the break, we went up to slide number 37. All right, so we're done with the 36, and we are done with the 37. All right, but you actually can see more examples from the iPad notes, which I kind of showed to you. Let's now talk about the global versus future operator. They turn out to be less trickier than the next operator in some way, but I'll show you some trick over here. Not really trick, some observation. Okay, so we're going to go over 4 pages. Let me just walk you through about the flow. The first 2 pages, we're going to talk about the global operator, G. And we start with path satisfaction for G. And then we go for model satisfaction for G. First 2 pages, right? The next 2 pages, we'll do future operator, path satisfaction. And then future operator and model satisfaction. We'll do these 4. Okay, we'll see how the time goes. Once we finish these, if we're pretty close to the end, I'll let you guys go. If not, then the next topic will be about how we can nest temporal operators together. I don't mind if we leave it until Monday to start fresh, but we'll see how that goes. Okay, but that'll be the next one. All right, let's now talk about one by one. The global operator. This one here is very straightforward. Basically, you will just check to see whether every state in the path will actually satisfy the formula. That's what you would do. All right? All right, so you can see that that's a definition. Just to remind you, if you say a path satisfy global, fine. That means every possible states in the path should really satisfy that. So let's say you're given this path over here, right? So here's an observation. For path satisfaction, if you want to check for the global operator, basically you want to see what are the reachable states from this particular path. And somehow you can see for the pi you're given, they're going to cover S0, S1, S2. Basically, they cover all the states. So this one tells you, once you figure out the set of reachable states, you only have to see whether each of the reachable states is going to satisfy the formula without a global operator. So that's the observation. Okay, I'm going to write it down. So by looking at the pi, here you can make some notes yourself. All the reachable states will be S0, S1, and S2. Of course, in this case, it covers all the states. But if I give you a different path, for example, if I give you just S0, S2, 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 the reachable states will be S0 and S2. Right? It's different. So it really depends. But in this case, we're going to check to see whether S0, S1, and S2, all the states, do they satisfy each of the formula? Right? Each one of them. S0, S1, S2. Okay? So what we're going to do is we already boiled down into just checking. So think about we're going to go for all these formula here. So you only have to check to see whether check these on the reachable states of the path. All right. Let's now check to see one of them, everyone. True will be satisfied by each one of them, by definition, right? And false is not satisfied. So We get true here, and we get true over here. All right. And then we got not P and R. You can feel free to apply De Morgan, right, to make it a little bit easier for you to read if that helps. So you can look at this one here. This one will be not P or not R. So we are asking whether every state will satisfy not P or not R. As long as one of them is true, then we're good. So for example, let's say not R is definitely satisfied by S0, right? Okay. And also not P is definitely satisfied by S1. And also not P is also satisfied by S2, right? You can see it's simply missing. All right. So this one here is also true. Of course, in the actual test or exam, you're just gonna say for S0, why does it not satisfy not P or why does it satisfy not P or not R? Right? That's something you're gonna say. I'll say, for example, I'll put one for you. For example, in S0, not R is true because R is missing. Okay, you gotta argue for every state. All right, and then here, let's say R. Is R satisfying every state? Not really, right? You can see, for example, here, R is already missing from here, right? It's definitely not. So you got to give a witness. And in the case of pi, what kind of witness do you give? Do you give a witness path or give a witness states? States, right? Right? You got to give a witness states. All right, this one is false, and then you're going to give a witness. And then you're going to say in S0, not R. Okay, that'll be enough. Okay, I think the reason I actually got here, repetition, I really meant to say pi to the power of 2. That's something for you to exercise. Okay. So what I will do is, let me just put it back over here. Okay, like that. And what you guys can try will be, I'll put the power of 2 right here for you to try. That'll be exercise for you. Okay. Which should be also very straightforward. But if you put pi 2, is it going to be all the state that's going to be reachable? Not really, right? Because S0 is gone. You only got S1 and S2 to consider. Okay. I'll just give you a little bit hints over here. For pi 2, you got to think about the set of reachable states. Will be basically starting from S1. So you got S1 and S2, right? So you can argue about these two states for the global property. All right, so that's about the path satisfaction. Let's now do the model satisfaction. Oh, Daniel. S0 reachable, yeah, no, because, good. You're quite right. According to the graph, you're right. S1, from S1 you can go to S0, that's true. But if you look at the path, that's not the path we're talking about, right? So here, once you get from here, you only got S1, S2, you're taking this path basically, right? Good question. All right. Model satisfaction. So what we're going to do is we're going to consider all the paths starting from S0. Okay, let's now first of all go by definition and we'll see what we can observe to make our make our task a little bit more efficient. So we talk about model satisfaction. All the paths starting from S0. And since we are talking about the global operator, right? All the paths starting from S0, you can also think about the reachable states. That's really the nature about the global operator. You want to talk about every state, right? So you want to think about here. So the reachable states from the path starting at S0 would be, well, everything. Because, for example, if you go for this path here, you can cover S0, S1. If you go to this path over here, you can already cover S1, S2, S1, S2, every state. So as long as you can be sure that every state in the graph will satisfy the property, you're basically done. It's just that when it is not satisfied, you have to give the witness path accordingly. Right? But when you try to check to see, you can only just look at the reachable states, just a little bit more efficient. All right, let's see how that can be argued. All right, the true and false, as before, right? They'll just be true. Doesn't matter. All right. And this one here, let me just rewrite it. We got not P or not R. All right. And that one, like before, right? Not P or not R. Not R is here, and not P is here, and not P is here, right? So that's true. All the paths. Okay. Because not P or not R is satisfied in all the states. All right. And now we know that this one here is not true, right? Because, for example, you can see R is simply just missing from here. Okay. However, you have to give a witness. You cannot simply say S0 is the witness. You got to say the path. All right. So here you're going to say, first of all, false. And then you got to give a witness. For model satisfaction, the witness should be a path. You can just give a path starting from S0. Well, you can say, for example, S0 and then S1, S0. And then you can say, well, the first state already violates R. Already. All right. All right, so let's see. The next one will be just exercise for you. Okay, you can give a try. All right, this will be exercise for you. You can see I changed that into S2. Meaning that we're going to consider all the paths starting from S2. Wow, that one actually seems to be a very simple path, right? That's a path considering reaching only S2. So all you got to check will be whether S2 will satisfy R. It would, right? This one here, we just did it together, okay? So this one here, you can think about S2 is the only reachable states for all paths starting at S2. Right? And we know that for S2, it satisfies R, so we're good. Okay? You can see somehow global operator is not as tricky as next because you don't really have to consider relative to the initial states, in which case, depending on the suffix I give to you, that can be a little bit tricky. But for global, you just got to think about where's the starting point, and from that point onwards, figure out the reachable states, and then you try to check for every state from there. The only thing you got to be very cautious about is, in the case of the model satisfaction, you don't give a witness states. You have to give a witness path. All right? Yeah? You mean S1? Sure. We can try. Are you suggesting, for example, S1 satisfy? What formula? The last one. Sure. Let's do it. Okay, if you think about S1 here, basically S1, you can either go to S2 or you can go to S0. You can reach to all the states, basically, right? So here you can see, first of all, the reachable states from S1 will just be all the states, S0, S1, and S2. And now you can see R, for example, is not really satisfied right here. Okay, so now we got to be careful. Okay, it's a very good question. it will be false. And what kind of witness path do you give? The witness path, you just cannot say, for example, S0, S1. You cannot say that. It's supposed to be a path starting from S1, right? Okay? So you can say witness. So I'll put it here. Starting from S1, and then S1, and then S0, and then S1. You can say that one of the states, S0 over here, does not satisfy R. All right? So I think that this example here is very valuable because that shows to you if you want to give a witness path, it's got to start from the states that you're checking about model satisfaction. Right? Here's a nice one. I'm glad you asked. Okay. So that's about the global operator. And let's now do two more. I got 3 minutes. Well, maybe we could do one more. Okay. Hey, future operator. Let's just do one more. I can leave the model satisfaction maybe next time. Okay, let's say this one here. The future operator in some ways even easier because you just want to find one state that's reachable and that will satisfy the formula, just one. And the witness tells you if you can find me a path, if you can, I'll get to the witness a little bit later. Okay. Let's just check. Let's say the pi that we're talking about is right here, S0, S1, S2. So reachable is all the states. So this pi here reaches S0, S1, and S2. All right. So all we got to do would be we just check to see whether each formula is going to be satisfied in one of the reachable states. That's the definition for future operator. That's all we got to do. All right. And true and false, no brainer, because you'll be satisfied by every state anyway. All right. Can we find a state where we got not P or not R? Okay, let's see here. There's one here. We're going to say not P or not R. I'm sure we can, right? For example here, right? S0, right? But that way you have to give, basically you want to show, okay, this is what you want to show. When you want to show the future operator, you want to say that for every path, there is at least one state that will satisfy that, right? That's a definition, okay? So let's now do this one here. You want to show that for every path, oh, sorry. I'm just getting myself confused about the model satisfaction. I do apologize. Okay, let me erase it. Okay, it's actually simpler. Since we're talking about this particular path, all we got to check is there a state that will satisfy this? That's it. Okay, in this way, we know that S0 satisfies it, so that's a witness. True, and then we just got a witness states. In that way, you can just give S0. That's it. For example, the first states. Because not R is there. Right? All right, let's finish them quickly. And then, is there a state satisfying R? Yeah, for sure. S2. S2. All right, is there a state satisfying Q and R? Indeed, S1, right? S1. All right, I think I'll pause here, okay? And then, so for next Monday, we're going to continue, and then we're going to do model satisfaction, and then we'll talk about nesting temporal operators. All right, thank you. I'll see you tomorrow.